So we've learned how to do stoichiometry, where we look at the amounts of reactants and products for a chemical reaction. If we have gases present, either as reactants or products, we generally don't specify their amounts as masses because gases are difficult to weigh. It's possible, but it's difficult. So we typically express the quantity of a gas in terms of its volume at a particular temperature and pressure. So we can use the ideal gas law to take that information and calculate the number of moles. So these are two rearrangements of the ideal gas law. We've used both of these in other problems. If we need to know the moles of gas are pressure volume divided by R times the temperature. If we've got the moles, say at the end of the calculation, we need to know the volume of the gas, we can use this version of the ideal gas law. When we're dealing with anything at STP, everything is simpler because we can use the molar volume of a gas. So if it says at STP, I always have like this inner cheer, yeah, because we can use this and it's easier. This works a lot like a molar mass, right? But it's a molar volume. And so we can calculate the molar volume of any gas using this relationship. The pressures that we see might also be partial pressures because there might be a mixture of gases involved. So what I've taught you is that stoichiometry follows this path, grams to moles to grams. And we've already seen a couple of variations when we had solutions instead of masses. And here we're just doing another variation. Here the reactant, instead of a solid that we can weigh, might be a gas. And so then we have a volume of the gas, and we also have to have specified the pressure and the temperature of the gas. So then to calculate the moles of the gas, instead of using a conversion factor, we're using the ideal gas law. At the end, we might end up with a mass, or we might end up with another gas. And so, again, we're going to have a volume, a pressure, and a temperature. Okay, so grams to moles to grams is the starting point, and then you see, do I need to change up the ends at all? So let's do an example. In the following reaction, 4.58 liters of oxygen was formed at pressure equals 745 millimeters of mercury and T equals 308 K. How many grams of Ag2O decomposed? So this is stoichiometry. We've got a chemical reaction and we're asking about quantities. So the chemical equation is given here. And I'm going to use that to organize the information. So I take this number, 4.58 liters of oxygen. And that pertains to oxygen, so I'm going to write it under oxygen in this chemical formula. I've got a pressure and a temperature. Which of these substances is that going to be important for? I have two solids and one gas. It's important for the gas, right? So I'm just going to write those here, 745 millimeters of mercury. Is that a good unit for gas law problems? Let's just convert that to atmospheres. 1 atmosphere divided by 760 millimeters of mercury. 745 divided by 760. 0.980. It is important here to at least keep the minimum number of significant figures. This has 3 Sig Figs. This is exact. This is now 3 Sig Figs, but I think it's a good idea to just write down 2 extra digits. I saw a couple of worksheet problems where people rounded too much and then the answer's not quite right. And so I took care of that number, and then the next one is 308 Kelvin. I also need that for the gas. Do I need to convert Kelvin? No. Kelvin is what I want. And then to the question, how many grams of Ag2O? Well, here's the Ag2O. I'm going to write a question mark here, and the requested unit is grams. So I pulled the numbers out, got rid of most of the words. That tends to help in turning this into a mathematical equation. So this is stoichiometry. So I'm going to think grams to moles to grams. At the end, I want grams, so this is good. At the beginning, though, I'm not given a mass. I'm given a volume, a pressure, and a temperature. Volume, pressure, temperature. Oops, that's an R. Can I use volume, pressure, and temperature to find the moles of the gas? Yes, I can. So then this is my path. So the first thing I have to do is use volume, pressure, and temperature to find moles of gas. So this is a little bit different because I'm not going to have just one long string with 3 factors because I have 3 arrows. This first one I'm going to do as an equation. So my first step is I'm going to use the ideal gas law, rearrange to solve for n. I didn't mean to put that there. Need to move that. Magic. Okay, so I've got the pressure, 0.98026 atmospheres, and the volume, 4.58 liters, divided by R, 0.08206 liter atmospheres per mole Kelvin. Remember, that's the ideal gas constant, and it's always the same because it's a constant. And the temperature, 308 Kelvin. So I need to be careful when I do this on my calculator. .98026 times 4.58 divided by 0.08206 divided by 308. And this is giving me 0.17763 moles. If you got a really large number instead of this number, you're having issues here. And you're seeing this as 0.08206 times 308. And if that's what makes the most sense to you, then this is what you need to do. You need to use parentheses when you do this, because you want to do the times there, then you have to put parentheses around both of the things in the denominator. If you do that, then you should get this number. So make sure that you can make your calculator show you the right number. Any questions about that? Looking at the units are all going to work out. That's always a good thing to check. Atmospheres cancel. Oops, the moles don't cancel. Liters cancel, Kelvins cancel. I'm left with moles. So this now is this part right here. So now I'm going to take the moles that I just found, and I can do my dimensional analysis. So 0.17763 moles of what? O2. So I am right here. And continuing on, there are two arrows, so I'm going to have two more factors here. I'm going to go from moles of O2 to moles of the thing I'm interested in. Moles of Ag2O. And in the denominator, I'm going to have moles of O2. That's just my unit, so the units cancel. And then I need another term. I'm going to grams. I need grams of Ag2O and moles of Ag2O in the denominator. Some of you are still not showing your units when you do the calculations, and I look and there's just a bunch of numbers multiplied and divided. And if you're getting the right answer, I still want you to show the units, but if you're getting the right answer, it's not going to be a huge problem. If you're getting the wrong answer, though, you really should write the units down, because they will help. Mole ratio, balanced chemical equation. 2 moles of this to 1 mole of that. So 2 goes in front of Ag2O, and 1 goes in front of O2. The last term between grams and moles is the molar mass. So I have 2 moles of silver. 107.9 is the molar mass of 1 mole of silver. .9, and there's 1 oxygen in there, so that's 16. 2 times 107.9 plus 16, I need 231.8. It's the molar mass of Ag2O. If I screw up, please yell out right away, because it seems to be happening more and more. So any questions about where I got the numbers, how I put those together? So now I just do these on my calculator. I'm going to start with the 0.17763 times 2 times 231.8. And again, I'm thinking about significant figures and looking around, seeing 3 Sig Figs. And I'm going to write down 2 extras. If you struggle with significant figures, just do 3 or 4. That's going to be fine most of the time. And so then I'm going to round this and say it's 82.3, and the units there are grams of Ag2O. Question?
I keep getting a different number.
Okay.
But I have the same.
Let me try it, because sometimes I screw up.
You got
82.349. It helps if your calculator will show you what you've typed in, so that you can just go back and look, because sometimes we miss a digit, or we get the wrong digit. So a couple things I've noticed in looking at your worksheets. I was just mentioning, well, 3 or 4 Sig Figs is generally safe. The one thing some of you struggle with is if you have a number like 0.00437, these zeros don't count. And so I'll see people write this down 0.004, and all I can think is that you must all I can assume is that you must think that's 3 sig figs, because it kind of looks like it. It's 3 digits after the decimal point. But this is only one significant figure. Yes?
Why did you put the 308K right there? Underneath the...
This 308K, that was the temperature I was writing down from up here.
Oh, so you don't...
Yeah, I wasn't using... That's a little confusing. So this was all pre-stuff. Does that help? And of course, this number is something I just made up right now. The other thing I see happening is that you've got all these calculations written out correctly. You showed your work. You've got all the units in there. Great. And then this number is something else. It happens, right? I think it happened to Lauren just now. What do? How do you avoid that problem? Because, you know, on a worksheet, if you show your work and there's some little glitchy thing, I'll write bad math and give you credit. On a multiple choice exam, if that causes you to choose the wrong answer, then it's wrong. You get nothing. So what you do is you want to, anytime you have a calculation like this, you want to punch it through on your calculator twice. Not just go back and look at it, but actually clear it and enter it in again. Because it's very unusual to make the same random error 2 times in a row, right? So if you get the same answer the second time, and that's what I did when you were like, I don't know, I got a different answer. I punched it through on my calculator again. I got the same number. You get the same number twice in a row, you're either making a consistent mistake or it's correct. If you get a different number, go for best 2 out of 3, right? Or go back and look at what you've done. It's very helpful, like I said, if your calculator can show you the things that you typed in. Some do, some don't. Any questions? Here's another example. This one's a little easier because of those wonderful letters at STP. So when it says at STP, then we know that there are 22.4 liters per 1 mole of gas. And that's true for any gas. So this question is asking us how many liters of oxygen at STP are required to form 10.5 grams of H2O. So I want 10.5 grams of H2O. And the question is how many liters of oxygen? The question goes here under O2, and we want liters. You have to identify where am I starting and where am I trying to go before you start traveling.
What's that little thingy back to?
This is the at symbol.
Oh.
It's not a very good one. Let me fix that. That better?
Yeah.
Yeah, there's a name with a circle around it. It just, I don't know what happened to it. So this is stoichiometry. Several clues about that. One is this word up here. But we have a chemical equation, we have a reaction going on, and we've got questions about how much. So grams to moles to grams is our starting point. And so here's the thing with the number, and that's grams. So we are starting with grams, we'll go to moles, and then the ending thing, we don't want grams, we want liters. So here, instead of grams, we're going to liters. We're not specifically given a pressure and a volume, but we're given at STP, and so this is going to be our conversion factor. If we were given another pressure and temperature, then we'd have to use the ideal gas law to do that last step. So 10.5 grams of H2O. I want to go to moles of H2O. I want to go to moles of the thing I'm questioning, wanting to find out about, O2. And then I'm going to go to liters of O2. Yes?
See, when I first read the problem, I was confused because I thought we were still going to use the PV equals nRT, because don't we assume that STP is 0 degrees Celsius and ATN?
Yes. So if you forget this number or forget that it even exists, STP does mean a temperature of 0 degrees Celsius, 273 Kelvin, and a pressure of 1 atmosphere. And you absolutely can still use the ideal gas law to do that. And, you know, if that's what you remember, then that's better than a shortcut you don't remember, right? Excellent question. I just realized that my liter here kind of looks like a C, and that is not carbon dioxide, L. So I've got the units on the top, grams to moles to liters. And then I'm going to fill in the units in the denominators, because the units are going to tell me what kind of numbers I need to put in here. So I got all the units worked out. They're going to tell me what to do. This first one, grams and moles. Grams and moles is always a molar mass. So I need the molar mass of water, 2 times 1.008 plus 16 gives me 18.016. So 1 mole weighs 18.016 grams. The mole ratio in the middle comes from the coefficients of the balanced chemical equation. 1 mole of O2 gives me 2 moles of water. So the O2 gets a 1 and the water gets a 2. It's just the coefficients. And then this last one, we can use the molar volume of the gas, 22.4 liters per mole. That only works at STP, but this is at STP. So 10.5 divided by 18.016 divided by 2 times 22.4. Three Sig Figs again. It's almost always 3 in these problems. So I'm going to write down 3, and then I'm going to write down the next 2. Don't have to worry about rounding when I do that. I just write them down. That's liters. And then I look here, I'm keeping the 2. The next digit is 7, so that means I need to round this up and call this 6.53 liters of oxygen. Any questions? Some of you are still resistant to doing dimensional analysis. And it's not the only way to do these problems, but I've been doing this for longer than most of you have been alive. And I've tried lots of different things with lots of different students, and I truly believe that this is the best way to do it. It involves the least amount of thinking. Thinking is great, but it can be time consuming, it can make your head hurt, and sometimes we think wrong. And so if there's a simple pattern we can follow, I mean, that's how you probably got to school today if you drove. You didn't think about every little step. Have you ever driven somewhere and you realize, I have no recollection of driving here, right? You're on autopilot, right? You're just following the same path that you always do, and your brain takes into account the stoplights and the traffic and stuff, and unless something interesting happened, you just get there and you're like, oh, here I am. And it can be the same way with dimensional analysis. It's a pattern. You just find the pieces, you start, and you go. Until that becomes familiar, until you understand how the pattern works, though, it's this mysterious, weird thing that I'm doing. You can get it, and once you get it, it really is a beautiful thing. But it may take some work and asking a lot of questions. So I highly encourage you to keep asking questions. Does anybody have any questions right now? I didn't think so. It's okay.